Everyone, and welcome. We are going to be talking about hypothesis testing for means. We're going to work through an example. Hopefully, you were able to watch the video that I put together on hypothesis testing overview in general. This problem focuses on averages. We also do hypothesis testing for proportions in this class, multiple averages, multiple proportions, but we're going to focus just on one sample means for this example. Now, the way that I approach this in my class is I have some specific guidelines, and in general, your teacher might structure it a little bit differently, but the idea is the same across the board. Costco claims that each can of sparkling water contains 12 fluid ounces. A random sample of 214 cans of sparkling water found the average number of fluid ounces to be 11.98, with a standard deviation of 0.12 fluid ounces. Do the data provide convincing evidence at the alpha equals 0.01 level of significance that Costco underfills their sparkling waters? What we have here is an assumption of truth and a claim that we want to test. The first part of hypothesis testing is to create a hypothesis. You need your null hypothesis and your alternative hypothesis in order to run your test. I will be using the convention of H0 and HA for null and alternative. Some people use a different convention of H0 and H1. So for us, we're going to be using H0 and HA. And our H0 is our assumption of truth. We believe some starting value of equality. Now, in null hypothesis, there is some texts that use a convention of less than or equal to, greater than or equal to, and we're not going to do that. We're going to follow what StatCrunch does and what our text does of assuming equality. So our null hypothesis is going to have an equal sign. Our alternative is the claim that we are testing. So we need to dive into this problem a little bit. Let's go back and reread and highlight the things that are important. Costco claims that each can of sparkling water contains 12 fluid ounces. A random sample of 214 cans of sparkling water found the average number of fluid ounces to be 11.98 with a standard deviation of 0.12 fluid ounces. Do the data provide convincing evidence at the alpha equals 0.01 level of significance that Costco underfills their sparkling waters? We are assuming that they do not underfill, and we are testing to find out whether they do underfill. Now, this problem is about averages rather than proportions. We need to pick the appropriate parameter symbol, and parameter refers to a population value. This question is about averages. We also work with proportions, but you need to make sure you pick the right symbol. Averages for population is mu. And if I put mu in my null hypothesis, I need to put mu in my alternative hypothesis. The symbol doesn't change. And notice I'm not using X bar. X bar is sample. I do not use sample data in my hypotheses. My hypotheses are about my population. Now, what am I assuming to be true? I'm trusting Costco. I'm trusting that they have 12 fluid ounces in their cans. And if I write 12 in my null hypothesis, I need to write 12 in my alternative hypothesis. And then I go to the claim. We want to know if they underfill, meaning less than. That's the symbol I put here. And you're either going to be using less than, more than, or different than, not equal to. Those are your symbols. Now I have my hypothesis set up. Great. What am I talking about? If I presented my hypothesis to somebody, they would not know anything other than 12 and average. But average what? Average hours of sleep, average number of hours on a phone, average ounces in a liter, that type of thing. So I need to define this. And mu refers to the true population mean of fluid ounces in a can at Costco. It's important that I include all of that information. I am talking about sparkling water. It could have been a soda. I'm talking about from Costco that is listed, and I am talking about fluid ounces. So it's really important that I include all of that. And I also like to state what our level of significance is. because that's going to help me make my decision later on. And a level of significance is how willing you are to make a type 1 error. I want to be certain within 1%. And what that means is I need the probability of obtaining the sample data that I did or data more extreme by chance to be less than 1%. So randomly, it could only have happened randomly less than 1% of the time. Otherwise, I don't have evidence. I need to check conditions now. So I've set up my problem. Now I need to check conditions because if my conditions are not met, my data is worthless. I need to have a random sample to be able to generalize to the population. And I need to have a normal distribution in order to be able to perform normal calculations. I need to be able to have that nice bell curve in order to actually use probabilities that we learned earlier in the semester. Checking random, for me, in our class, it's nice and tidy with a little bow. It's going to tell us that it's random, or you're going to have some random assumption. It may not be in the real world, but for now, you either need to have it given to you or not. And here it was stated to be random. You could also call the normal condition the large condition. The way that we check normal, excuse me, for proportions and means is different. For means, there's actually three different ways that we could check the normal distribution. First, we could be told that our population is normally distributed. In the real world, not really realistic, because if you know that your population is normally distributed, then maybe you already have the data that you need and you don't need to perform inference. But again, it could be given to you in a problem because we're setting things up nicely. Or you can use the central limit theorem to determine based on sample size whether your distribution was approximately normal. So central limit theorem, which comes from calculus, essentially states that once your sample gets to be above 30, then our sampling distribution is going to be approximately normal, and we can use normal calculations. Remember, when we're talking about a normal distribution, we're looking at something that is unimodal and symmetric, not the best drawing, but you get the idea. We are assuming that 12 is the actual average value, and then we're trying to determine how likely it was that we got 11.98. Now, because our sample size was more than 30, we're okay to use normal calculations. The third method is if your sample size is not large enough and the population is not stated to be normally distributed, then we need to be either given the entire list of numbers or the fact that the graph has no outliers or strong skewness. So if our graph is approximately symmetric, then we should be okay. That's third situation. Now our conditions are met, we're going to perform some calculations, and this is when our sample data comes in. It's important to note that for means, we actually need to know the population standard deviation in order to calculate a z-score. Because if you do not know the population standard deviation, based on the sample size, the distribution changes. When you have a smaller sample size and you don't know the population standard deviation, the sampling distribution actually has fatter tails and is squatty. And as the sample size goes up, your distribution becomes more and more approximately normal. And so we have degrees of freedom, we have some differences here. So we're actually going to calculate a t-score instead of a z-score because we are not given the population standard deviation. So we will be calculating t-stat. In order to calculate t-stat, we're actually going to use StatCrunch. I will show you how to do it by hand, but it's much better to let the computer do it for you because if you're doing it by hand, you need to calculate the test statistic and either use a t-calculator to determine the probability or a t-chart. Now, I know that I'm not using charts and I feel like most of the people in my department are not using charts. You might have used charts when you were in high school, but when we're using larger data sets, it's better to use computers because when you go out in the real world, that's what's going to really happen. I know that my sample average was 11.98 and my sample standard deviation was 0.12. And what I want to do is I want to determine what my test statistic is, and I want to determine what my p-value is. The test statistic is the t-score, and the p-value is the probability based on that t-score in your direction of obtaining the sample data you did or data more extreme if it really was that Costco had 12 ounces in their cans. The test statistic that we are calculating takes the sample mean minus the population mean over the sample standard deviation divided by the square root of the sample size. That's going to be 11.98 minus 12 divided by 0.12 over the square root of 214. You need to follow the order of operations in order to calculate this correctly. Otherwise, your calculator is probably, if you don't use parentheses, it's going to do some funky stuff. But this calculation is negative 2.438. But let's use StatCrunch to determine that, because then I need to know what the probability is of obtaining that. Negative 2.438 is essentially telling me that I'm about here on my distribution. I'm 2.4 standard deviations below average. And how likely is that? You should have an idea based on the 68, 95, 99, 7 rule about how likely that is. Because remember, 95% of the population falls within 2 standard deviations, and we're outside that. All right, so I'm going to hop over to StatCrunch. And I am going to go to stat. All of our calculations live in stat. I'm doing, again, a t-stat because I do not know the population standard deviation, and I only had one sample of 214 cans. With data means I had 214 averages or 214 fluid ounces given to me of the cans. We have with summary where we were told already what the average and the standard deviation was for that group. The sample mean was 11.98. The sample standard deviation was 0.12, and the sample size was 214. Now, if you get into a calculator and you have too much information or not enough information, you're not in the right place. We're not using applets. We're not doing some sort of interval simulation. We're actually using a calculator to determine this information. Now I need to adjust the hypothesis test to match the value that was claimed to be true, and then test the direction that I want. So this hypothesis should match what you've written on your paper. You should have sample mean 11.98, sample standard deviation of 0.12, sample size of 214. We change the value to 12, and we have a less than. Now I'm running a hypothesis test, so I've clicked hypothesis test. If I was doing an interval, that would be different. So now I'm going to compute. And you can see here that my hypotheses matched what I had written on my paper. I'm given mu, which is the parameter symbol, the sample mean, the standard error, which is 0.12 divided by the square root of 214, the degrees of freedom, n-1 for one sample, and then t-stat and p-value. Those are the two that are important for us. So we need that negative 2.438 and that 0.0078. Notice what I calculated by hand matched, but I don't get a p-value from calculating by hand. In order to get a p-value, I actually need to go to stat, calculators, and t. I need to pull this up so I can calculate the distribution. And I needed the degrees of freedom, so you need to know how to calculate n-1. And then you have to put in your value for the t-value. Negative 2.438. And I compute. And notice I get 0.007799424. But in order to do this, I had to know how to calculate the test statistic by hand and then get the calculator. I could have used a t-chart. I'm not going to demonstrate that here. But I get the same value for the p-value. That's where it comes from. It's the probability. And remember, that means that 0.78% is how often I would obtain this sample data or sample data more extreme purely by chance if the null really was true. Very small. What I do then is I make a conclusion. And when I'm making a conclusion, if that probability is small, that means I have evidence. So I'm not believing Costco and I'm believing they're underfilled. If the probability is not small, then I don't have evidence and I'm not rejecting Costco's claim or Costco's assumption of truth. Now, how strong my evidence needs to be is that level of significance. And again, it's how willing you are to make a type 1 error. There are certain situations where you need to be really, really strict with that level of significance when your consequences of a type 1 error are pretty extreme, but that's a little bit beyond what we're doing in our course. So for now, we're being told kind of what would be an appropriate level at this point. Our alpha level was 0.01 or 1%, and our p-value was 0.0078 or 78 hundredths of a percent, so 0.78%. And that p-value is smaller than our alpha level. It's very small. So since our p-value is less than our level of significance, what do we do when our p-value is small? If our p-value is small, it means it's rare, unlikely to happen by chance alone, and we have evidence. So if that's true, I'm rejecting Costco's claim of 12 ounces. Claim is the word typically that we use for the alternative, but I'm rejecting Costco's statement that 12 ounces are in the can. And if we reject the null, that means we have evidence to support the actual claim of underfilling. And this statement is not enough. I need context. And there you have it. I have performed an inference procedure, a hypothesis test for means using my four-step process that I like, but I make a statement of what I'm doing. I check conditions, I run the numbers, and then I make a conclusion based on that. Thank you for watching.